heat conduction problem, bar with insulated ends. So we need to derive the solution for this heat conduction problem, and we have PDE, that's equation 1, boundary conditions. Okay, these are due to the insulated ends. So ends of the bar are insulated. So we have something similar to this, and the heat conduction through ends are 0. I mean, there are none. That means these are zeros. And the initial temperature distribution, that's the initial condition, is ux0 equals fx. Okay, and we use the method of separation of variables, for we let uxt be x t, let's say number 4, be the solution. Okay, now we plug this 4 into this PDE 1 and we get two ordinary differential equations. Plug 4 into 1, we get, so alpha square uxx. So we are supposed to find the partial derivative of u with respect to x. So in the right hand side we have single variable functions. So when we find derivative with respect to x, this behaves like a constant, so this becomes x double prime as a x. I'm dropping that part, t. That's the left hand side, is equal to ut. X behaves like constant, t with respect to t, so t prime. Divide both sides by alpha square x and t. We get x double prime over x equals 1 over alpha square t prime over t. Okay, in the left hand side, this is a function of x, this is also a function of x, function of t, but their ratios are equal. I mean, this is constant. That means each ratio should be a constant, and we say, let's say this be negative lambda. Then we said the first fraction equals negative lambda. First fraction equals negative lambda. That gives us x double prime plus lambda x equals 0, 5. And second fraction equals negative lambda, cross multiply. At the end of the day, you get t prime plus lambda alpha square t equals 0. That's equation 6. Now we want to solve 5 and 6 for these boundary conditions and initial condition. But 5 is only in terms of x. So what we do all the time, we plug 4 into these boundary conditions. Okay, let's do that. Then hope we'll get boundary conditions in terms of only one variable. Plug the assumption 4 into the boundary conditions. Let's put that is ux0 t equals 0. We get, note that to plug 4 into this, we need to find the partial derivative of 4, because this is only u, but our boundary condition is ux, so we need to find the derivative with respect to x. So let me find that. Ux, okay, is coming from 4. When we differentiate right hand side, partial derivative with respect to x, just normal derivative, because these are just single variable functions, x prime t. X prime is a function of x and t is a function of t. Okay, using this, that equals 0. So x prime x, t x is 0, by the way, so this is 0. Equals 0. Okay, so we got a product of two things equals 0. That implies either x prime 0 equals 0 or t t equals 0, and this is for all t. But t equals 0 for all t means our solution u will be a trivial solution, because this will be 0. If we take t is 0, this is 0 all the time for all t, then this becomes 0. But this x prime 0 equals 0, that's just from one point, so this is not bad. So this implies x prime at 0 equals 0. Okay. Similarly, if we plug 4 into the second boundary condition here, okay, let's try that. Similarly, okay, we get from the second boundary condition, by the way, we should get x prime at the right end, that's the L, equals 0. So we solve the boundary value problem 5 with respect to these two boundary conditions. Okay, 5 and I'll say 6. Okay, now we solve the boundary value problem 5 with these two boundary conditions, x prime at 0 equals 0, x prime at L equals 0. This is 5, let's say these are 7. Okay, now we need to consider 3 cases. Okay, because lambda, this could be a positive number, 0, or negative number. So 3 cases. Okay, let's take lambda less than 0, and we can say lambda be, let's say, negative. Less than 0 means of mu square, where mu is positive, so whole thing is negative. If we say that, then 5 becomes, x double prime minus mu square x equals 0. Now we know how to solve this. We find the characteristic equation, that's r square minus mu square equals 0. So r, move that over, so plus minus mu. Okay, that means x as a function of x is, when we have two real and distinct real, but these are same real roots, we get in terms of hyperbolic function. So let's say k1 cosine hyperbolic mu x plus k2 sine hyperbolic mu x. Okay, and to make use of these boundary conditions, we need to find the derivative, and x prime, okay, derivative of cosine hyperbolic is just sine hyperbolic, and this mu from chain rule, mu k1 sine hyperbolic mu x, mu outside k2 cosine hyperbolic mu x. Okay, now using x prime 0 equals 0, we get x prime x, that's 0 equals 0, mu k1 sine hyperbolic 0, sine hyperbolic 0 is 0, so this is 0, plus mu k2 cosine hyperbolic 0, because we are replacing x by 0, and cosine hyperbolic 0 is 1, so this is 1, so mu k2. So we are finding mu times k2 equals 0. By the way, mu is positive, so this is not 0, that implies k2 0. Okay, using the first boundary condition, let's use the second one. Using x prime at right and L equals 0, we get, again we use here, right, in this case. So x prime at L equals 0 equals k2 is 0, so we don't have to consider the second part. K2 is 0, so mu k1 sine hyperbolic mu L, and this is not 0, and we know that sine hyperbolic is 0 at only one point when this is 0, but this is not 0. Mu is positive and L is also positive. That's the length of bar. So this is not 0, mu is not 0, that forces the constant K10. So K10, K20 means our solution, which is here, this is the solution, is trivial solution. That's lambda less than 0 is not an eigenvalue. Okay, so we have the solution in this case, x is just 0, trivial solution. So we disregard this case, so there will be no solution, so non-trivial solution in this case, lambda less than 0. So case 2, let's take lambda 0. When we take lambda 0, then equation 5 becomes x prime equals 0, and we want to solve this with respect to these boundary conditions. Then 5 becomes x prime equals 0. Now integrate, we get x prime equals some constant, let's say again k or a. Integrate one more time with respect to x, we get x equals a x plus b. Okay, this is uppercase x is a function of little x, this is little x. And now we need to use the boundary conditions from 7 for we need to differentiate, which is here by the way. When we use these boundary conditions, we need to use this function, and this is the solution. Let's try to find the values of a and b. So using x prime at 0 equals 0, we get, so basically we are using this part because the derivative, x prime at 0 equals a, so a is 0. So the solution is, this part is 0, x equals just b, a constant, but we have had to use the second boundary condition. Let's use second, x prime L equals 0. Using x prime at L equals 0, we get here x prime at L is 0, and there is nothing to plug in, just the pure constant, so we again get the same thing, a equals 0. Thus the solution in this case, which is sometimes called eigenfunction, the solution is x as a function of x equals a is 0, just b, just a constant, or simply we can say x equals just b, or just x is 1. Okay, so lambda equals 0 is an eigenvalue in our case, and the solution is a constant solution, and we are taking 1. Now case 3, where lambda is positive, and lambda is positive, we can say lambda be, just say mu square. Okay, then 5 becomes the ODE. We have x double prime plus lambda x, lambda mu square x equals 0, and we can find the characteristic equation for this ODE. That's r square plus mu square equals 0. Move this over, then r is plus minus mu I. Okay, so the solution is x as a function of x is k1 regular cosine, because we have I, cosine mu x plus k2 sine mu x. But our, look at 7, I meant 7, they are given in terms of derivatives, so we need to find the derivative. X prime x equals derivative of cosine is negative sine, so mu k1 sine mu x plus mu k2 cosine mu x. Using 7, that means x prime at 0 equals 0, we get 0 equals, now x prime is 0, so we are replacing x by 0. Sine 0 is 0, so this is just 0, plus mu k2 cosine 0, which is 1. So mu k2, mu is positive, look at here, so this forces k2 be 0, because we got a product of two things 0 and mu is not 0, that means k2 is 0. And using this second boundary condition, which is x prime at the other end L equals 0, we get, so we are using this, okay, so this is 0 equals k2 is 0, so we don't have to consider the second part, just the first part, minus mu k1 sine mu L. Okay, mu is positive, so this is, we got a product of three things 0. Okay, if we take k1 0, then we get trivial solution, but note that sine is 0 at certain points, so we are saying now mu positive is not 0, and now we want to make k1 not 0. Okay, let's make k1 not 0. That forces us to take sine mu L equals 0, and this is true in some cases. And we know that sine theta is 0 when theta is n pi, plus minus n pi, but we are considering lambda positives, so we just take the positive ends. So this implies mu L equals n pi, n bigger than equal to 1, 1 2 3 4 etc. That means mu is n pi over L. So for this mu means lambda is mu square, that is lambda equals mu square, so n is square pi is square over L is square. And not only we got one lambda, we got n 1 2 3 4, so we have to put lambda n. So for these lambda n's we have solution. Okay, and what is that? What is the solution? Those are called eigenfunctions, and solution was pretty much given from here, and we found k2 0, so this, there is no second term, just the first term, and we get x equals k1, just the arbitrary constant, cosine mu x, cosine, and mu is found here, n pi over L, n pi over L x, and there are infinitely many, so we need to put n here as well. And now constant times a function, we can simply take the constant to be 1, or x n, the solutions are, just take 1 cosine n pi over Lx for n bigger than or equal to 1. Okay, so these are the non-trivial solutions. So we are halfway done. We found the x. Now we want to solve the equation 6. Okay, that's t, and the product of x and t is the solution. So recall the 6. Okay, now we want to solve 6. Okay, that was, let me go back, that was all t prime plus alpha square lambda, or lambda alpha square, same thing, t equals 0. This is true for all lambda, but as we just saw, there are certain lambdas for which x is non-trivial. So if we go up, we found that when lambda is 0, we get non-trivial solution, which is just a constant, but it's still non-trivial solution. And we know that when lambda is positive, but specifically n square pi square over L square, and we get solution. So we have to consider both cases. Okay, so for lambda equals 0, then equation 6 becomes t prime equals 0. Okay, this is 0. That implies t is constant, because when we integrate both sides with respect to t, we get t is constant. Okay, any constant, let's say d1, just d, and we can simply take 1 for constant, or simply t equals 1. Okay, t as a function of t, maybe let me write t as a function of t is just a constant. Okay, and for lambda equals, here we also got non-trivial solutions when lambda equals this. Lambda, in fact lambda n equals, because there are more than one n square pi square over l square, equation 6 becomes here t prime plus alpha square, lambda is here now, n square pi square over l square t equals 0. Now let's solve this equation. Let's move this over. So we get t prime equals negative alpha square n square pi square over l square t. Move this t to the left side. That means we can divide by t. Integrate both sides with respect to t. So this becomes ln t. Okay, this becomes ln t equals that times t plus constant. Okay, and exponentiate both sides. Ln t is just t. So this is t as a function of t equals some constant, let's say d2, e raised to negative alpha square n square pi square over l square t. I mean, this is like, let me show you here. We have like t prime over t equals, this is some constant, let's say negative k. When we integrate both sides, we get ln t equals negative kt, okay, plus some constant, and exponentiate both sides, we get t equals e raised to negative kt times, because this plus means when we exponentiate, this becomes e raised to k2, and this is a constant, and I'm writing that as d2 and e raised to negative kt. Okay, and that means t is proportional to this function, and we can always take d2 to be just a constant 1, okay, or t, and look, we have infinitely many n's, so we have to put n, tn equals e raised to negative alpha square n square pi square over l square t, just taking d2 to be 1. So this is another solution, t when lambda is this. So now we want to find the solution u, because that was the case. Thus u ext, at the very beginning we assumed in equation 3, now equation 4, u was ex times t, okay, and that is, thus that becomes, we have two cases by the way, u when the lambda is 0, okay, we got that part, and when lambda is n square pi square over l square. When lambda is 0, so let's say u0, x was just 1, because we just said 1, constant function times 1, so 1, and for all other n's, n 1 2 3 4 etc., that was xt. So x was found here, just the cosine function, okay, and for these x, those are coming from lambda n's, and we found t here. So cosine, let me write this first then, e raised to negative alpha square n square pi square over l square t times cosine n pi x over l, or n pi over l x, and these solutions are, by the way, fundamental solutions. They form a set of fundamental set of solutions. Then how do we write this general solution? We just take the linear combination of these solutions. So general solution u ext is, by the way, linear combination. For first we have just 1, so constant times this solution, and we just take constant to be c0 over 2 times 1 plus, there are infinitely many, so c1 times first plus c2 times second, so we write in this way, n from 1 through infinity cn of this e negative alpha square n square pi square over l square t times cosine n pi x over l. Okay, this is the solution, general solution, where c0 and cn's are unknowns. And remember, we have yet to use the initial condition, equation 3. If you go all the way up, you'll see we haven't used initial condition. That's equation 3. Okay, now using equation 3, that was, by the way, u x0 equals some function fx. We get, so u x0, when t is 0, so this u becomes fx. We get the function equals, so I'm using here, c0 over 2 plus sum n from 1 through infinity, t is 0, so e raised to 0, that's 1, so we have cn cosine n pi x over l. And by the way, this is, which is the Fourier, by the way, Fourier cosine series, Fourier cosine series for the function f, which has the period of 2l. Okay, and we know how to find the constants c0 and c1, c2, etc. Okay, that implies cn's are given by, we can find all cn's in one place starting n equals 0, 1, 2, 3, 4. That is 2 over l integration 0 to l, this function, and just cosine n pi over l x dx for all n equals 0, 1, 2, 3, etc. And the solution for this problem, okay, is in fact given by this u. This is the solution anyways, u star, let's say star, where these cn's are found using this, for n equals 0, 1, 2, 3, 4, etc. star 2. Okay, hence the solution of the original problem, heat conduction problem, is given by star, where those constants cn's, n is 0, 1, 2, 3, 4, etc. are found using double star. Final.